Hello friends, welcome to lecture series on essential mathematics for machine learning. In the last lecture we have seen that what convex sets, convex functions are and some of their properties. Other properties of convex function we will see in this lecture. So, let us try to understand what are the other properties of convex functions. So, before stating the other property of convex function, which is a very important property of convex function, we first define that how we can what do you mean by definiteness of a matrix. When we can say that a given square matrix, given square symmetric matrix in fact is positive semi definite, positive definite, negative semi definite or negative definite. So, here is the definition: a symmetric matrix H of order n cross n is said to be positive semi definite if x transpose H x is greater than or equal to 0 for all x belongs to R n. If this sign is reversed, that is less than or equal to 0 for every x belongs to R n, then this is called negative semi definite. Positive definite if x transpose H x is strictly greater than 0 for all x belongs to R n and x not equal to 0. Okay. This hold as strict sense, and for every x belongs to R n and x not equal to 0. And if again this inequality reversed, that is it is less than 0 for every x belongs to R n and x not equal to 0, then it is called negative definite. So, from this definition, from these 4 points, one thing is clear that if H is negative semi definite, then minus H is positive semi definite, because there is a sign of only this inequality is reversed. And similarly, if a matrix is positive definite, then minus H is negative definite. So, here is a remark that a symmetric matrix H is negative semi definite or negative definite if and only if minus H is positive semi definite or positive definite. So, let us discuss these things by an example. Suppose we are having this example. Suppose we have matrix A which is given by suppose 3 1 1 3. So, it is a 2 cross 2 matrix and of course, it is symmetric because A equal to A transpose. Okay. Now, to check whether this matrix is positive semi definite, negative semi definite or positive definite or negative definite, what we find? We find x transpose A x. Okay. What is x transpose? See, this is 2 cross 2 matrix. So, it will involve 2 component x 1 and x 2. A is 3 1 1 3 and this is x 1 x 2. Now, when you multiply this, so this is x 1 x 2, this is so here x is what? Here x is x 1 x 2 transpose. So, this row, this column gives 3 x 1 plus x 2, it is x 1 plus 3 x 2, and when you multiply this row with this column, this is simply 3 x 1 square plus x 1 x 2 plus x 2 x 1 plus 3 x 2 square. So, this is nothing but 3 x 1 square plus 2 x 1 x 2 plus 3 x 2 square, and this is further can be written as twice of x 1 square plus x 2 square plus x 1 square plus x 2 square plus 2 x 1 x 2, okay, because it is 3 x 1 square plus 3 x 2 square. So, this is further written as 2 x 1 square plus twice of x 2 square plus this is x 1 plus x 2 whole square. So, now from this we can easily conclude that this is always greater than or equal to 0 for all x belongs to R 2. Here x is in R 2, okay, and this is 0 only when both are 0, that means x 1 x 2 both are 0. Okay. So, for every x belongs to R 2, this quantity is always greater than or equal to 0. So, we can say that this matrix A here, whatever A matrix we have chosen, this matrix A is nothing but positive semi definite matrix. Okay. So, we have concluded that this matrix A is positive semi definite. Okay. Now, in fact, this matrix is positive definite. Why I am saying this? Because it is 0 only when x equal to 0. X equal to 0 means x1 x2 both are 0. So if you go to a definition, then if you go to this definition that x transpose Hx is greater than 0 for all x belongs to R and x not equal to 0. Whenever x is not equal to 0, x is not equal to 0 means x1 x2 are not equal to 0 0. So, if x1 x2 are not equal to 0 0, this is always strictly greater than 0. So, this matrix is in fact positive definite. Okay. So, now consider another example, say consider this example 2 minus 2 minus 2 2. So, suppose this is M. Again this matrix is of order 2 cross 2, it is a symmetric matrix because M equal to M transpose. Now, again you consider x transpose M x, which is x 1 x 2, M is 2 minus 2 minus 2 2, and this is x 1 x 2. So, this is nothing but x 1 x 2 and this is 2 x 1 minus 2 x 2. This is minus 2 x 1 plus 2 x 2 by the matrix multiplication, and it is 2 x 1 is square. This x 2 multiply by this row, this column, that is 2 x 1 x 2, 2 x 1 x 2, that is minus 4 x 1 x 2 and plus 2 x 2 square. So, this is nothing but 2 of x 1 minus x 2 whole square, and which is always greater or equal to 0 for every x 1 x 2 belongs to R 2. So, what we have concluded from here? We have concluded that this matrix M is nothing but positive semi-definite. So, this implies M is positive semi-definite. So, here there are some non-zero x also. For this particular example, there are some non-zero x also where it is 0. Okay. For example, 1 1, 2 2, whenever x 1 equal to x 2. So, these are not 0, but still this value comes out to be 0. So, it is not positive definite, but it is positive semi-definite. Okay. So, in this way we have seen that these are the few matrices of square matrices, symmetric matrix, which are positive definite or semi-definite. In the same way we can proceed for negative semi-definite. So, now the question arises that if a matrix is given to you, these examples I have taken only 2 cross 2 or 3 cross 3 we can see, but if it is a n cross n general matrix, then how we can check whether a given matrix is positive semi-definite or negative semi-definite, how we can see. So, what are different tests? So, we have different tests. The test 1 is eigenvalue test. So, what this test is? So, let A be a real symmetric matrix of order n, then A is positive definite if and only if all its eigenvalues are positive. So, you find eigenvalues of a given matrix A, given symmetric matrix A, and if all eigenvalues are greater than 0, then the given matrix is positive definite. Semi definite if and only if all its eigenvalues are greater than equal to 0. Negative definite if all eigenvalues are, if and only if all its eigenvalues are negative, less than 0, and negative semi definite if and only if all its eigenvalues are less than or equal to 0. And indefinite if and only if there is at least one positive eigenvalue and at least one negative eigenvalue of A. Okay. So, this is the first test. You find the eigenvalues of a given matrix, given symmetric matrix A, and if all eigenvalues are come out to be strictly greater than 0 means positive definite, greater than equal to 0 that means positive semi definite, less than 0 means negative definite, and less than equal to 0 means negative semi definite. This is the first test. Now, of course it is a symmetric matrix. So, all its eigenvalues will be real, then only we can talk about positive or negative. Okay. Of course, that will of course holds because it is a symmetric matrix. Now, again finding eigenvalues of a large matrix, say 10 cross 10 or a 5 cross 5 matrix, is not an easy task. So, how can we proceed? What is a simple test by which we can say that a given matrix is positive definite or negative semi definite or whatever? So, we have another test, that is test 2, which is called minor test. So, let us see what first of all what do you mean by minors, and then we will go for minor test. A principal minor dk of a matrix A of order k is a determinant of the matrix formed by deleting any n minus k rows and n minus k columns with the same number. So, what do you mean by this? We will discuss it by an example. So, and first of all I have to read this principal minor test. So, what this test is basically, the necessary and sufficient condition for a symmetric matrix to be positive semi definite is that all the possible principal minors should be non negative, that is should be greater than or equal to 0, and for positive definite should be strictly greater than 0. So, let us discuss it by an example, so that things will be clear to you what do you mean by principal minors and what are different tests. Now, suppose you have this example. Let us take M as 4 2 3 2 3 2 3 2 4. So, first of all, is it symmetric? Yes, it is symmetric, because you can easily verify that M equal to M transpose, a symmetric matrix. Now, to check whether this matrix, what is the nature of this matrix, is it positive definite, negative, or neither, how we can check. So, the first of all, either you can find out the eigenvalues of this matrix. So, by finding the eigenvalues you can say whether this matrix is positive definite or whatever, or negative definite or semi definite. The other way out is you find out the minors of this. So, first of all we find out the, it is a 3 cross 3 matrix. So, first of all you find minors of order 1 cross 1. So, how you find minors of order 1 cross 1? Okay. So, you see, you delete second row and second column, you delete third row and third column. What is left with us? 4, and the determinant of 4 is 4 itself. So, it will come out to be 4. Okay. So, here k is 1 and n is 3, you see here. If you see here k is 1 and n is 3. So, 3 minus 1 means 2. So, you delete any 2 rows and any 2 columns with the same number. Okay. I mean the same column and same rows. Okay. If you are deleting second row, second column, third row, third column, you are left with 4. So, 4 is the first minor. Now, if you delete first row, first column, sorry, and second row, second column, you left with 4, this 4. So, this is a second minor of 1 cross 1. Now, if you delete third row, third column, and first row, first column, so you left with 3. So, this is 3. So, basically minors of order 1 cross 1 are nothing but diagonal elements. So, diagonal elements are 4 3 4, 4 3 4. So, here all are greater than 0. Now, let us compute minors of order 2 cross 2. So, now k will be 2 and n is 3, order is 3. So, 3 minus 2 means 1. So, you will delete one row and the corresponding column, and whatever determinant you will obtain, that is a determinant, that is a minor of order 2 cross 2. So, let us try to compute. So, first of all, suppose you delete first row and first column. So, you will left with this. So, you will left with 3 2 2 4. Okay. Now, suppose you delete second row and second column. Now, you left with 4 3 3 4. Second row and second column. So, you left with 4 3 3 4. Okay. Now, you delete third row and third column. So, you will left with 4 2 2 3. Okay. Now, what is the determinant of this? The determinant of this is 12 minus 4, that is 8. What is the determinant of this? The determinant of this is 16 minus 9. 16 minus 9 is 7. The determinant of this is 12 minus 4, 12 minus 4 is 8. So, it is 8. So, again here also the all the principal minors of 2 cross 2 are greater than 0, 8, 7 and 8. Now, only one left, that is minor of order 3 cross 3, which is the determinant of the matrix itself, which is what 2, 4, 2, 3, 2, 3, 2, 3, 2, 4. Now, what it is? It is 4 times, you delete this row, this column, you find a determinant basically 12 minus 4, it is minus 2, that means 8 minus 6 and that means plus 3 times 4 minus 9, that is equal to, that is 8 into 4 is 32, 32 minus it is 4, it is minus 5 minus 15. So, this value is in positive of course, and 32 minus 19 is positive. So, we can say that all the minors 1 cross 1 all the possible minors, 2 cross 2 all the possible minors, 3 cross 3 only one possible minor in this case, and all are strictly greater than 0, that means this matrix M is positive definite. So, this implies M is positive definite. Okay. So, this is what given in this necessary sufficient condition, that you find out all the possible principal minors, and if all the possible principal minors are strictly greater than 0, that means matrix is positive definite. If it is greater than equal to 0, that means positive semi definite, and for negative definite it should be all minors should be not all. See, for negative definite or negative semi definite, you first convert into, you first multiply that matrix with minus 1 and then test for positive definite or positive semi definite, because otherwise sign will be alternating. If you see for say if you are seeing for negative semi definite, then the first order minors of order 1 cross 1 are less than 0, minors of order 2 cross 2 are greater than 0, minors of order 3 cross 3 are less than 0 and so on. Okay. Or the other way out is you convert, you multiply the matrix by minus 1 and check for positive semi definite or positive definite, that is quite easy. Okay. So, now let us come to the property of convex function. Now, we have already seen the basic definition of convex, that when we can say the function is convex. We have already also seen that if a function is once differentiable on a open convex set S, then an inequality hold, that also we have discussed. Okay. But if a function is twice differentiable suppose and it is convex, then what is the important property? Important property is given in this theorem. What is that? Let S be a non-empty open convex subset of Rn, and f is a function from S to R be twice differentiable on S. Then f is a convex function on S if and only if the Hessian matrix, which is del square of f x, is positive semi definite for every x belongs to S. So, if this matrix is positive semi definite, the function is always convex, or if function is convex, then this matrix is always positive semi definite. So, this is very important theorem for checking whether a given function is convex or not. Okay. So, let us discuss the proof of this. Okay. So, those who are interested can see the see the proof, otherwise in terms of machine learning, if you know the result also, then it is also sufficient. Okay. But here I am discussing the proof for those who are interested. So, we have to show that f is convex if and only if del square of f x is positive semi definite for all x belongs to S, where it says S is an open convex subset of Rn. So, let us discuss the proof. So, first let f be a convex, f is convex on S, f is a f be a convex function on S. So, if you want to show that this matrix is this Hessian matrix is positive semi definite, what we have to show? We have to show that taking any, let x bar belongs to S, if we take a point x bar belongs to S, then we have to show that x bar belongs to S, then we have to show that x transpose gradient square of f x bar into x is greater than or equal to 0 for all x belongs to R n. See, we have already seen that when a matrix is said to be positive semi definite, here instead of m we have del square of f x bar. So, x transpose m x should be greater than or equal to 0 for every x belongs to R n. If this holds, then we can say that the given matrix is positive semi definite. So, since x bar is an arbitrary point on S, so if we have shown this for x bar, that means we have shown this for every x bar belongs to S. Okay. So, let us try to prove this inequality. So, now since S is open, it is given the statement itself. If you see the statement, it is given to us that S is an open convex subset of R n. So, since S is open, therefore, for any given x belongs to R n, there exists some lambda bar such that for 0 less than lambda bar, x bar plus lambda x will belongs to S. Okay. No matter how small lambda bar is, it hardly matters, but there will exist some lambda bar such that for any x belongs to R n, x bar is already in S. So, this x bar plus lambda x will be in S, because S is open. Okay. One can very easily visualize the geometry of this. Now, let us use the second order differentiability of f at x bar. So, since f at x bar is second order differentiable, it is given to us. So, what we have, it is x bar plus lambda x will be equals to f x bar plus lambda x transpose gradient of f x bar plus 1 by 2 lambda x transpose gradient square of f x bar into lambda x plus beta, it is x bar lambda x norm of lambda x whole square. So, this we have already discussed in the last lecture, that what do you mean by twice differentiability of f at x bar. It is some see, it is x 1, it is x 2. If we are talking about differentiability of f at x 2, that means f x 1 equal to f x 2 plus x 1 minus x 2, which is lambda x here, gradient of f x bar plus half of x 1 minus x 2 transpose gradient square f x bar lambda x plus beta times x 1 minus x 2 into x 2 and norm of x 2 minus x 1 whole square, or x 1 minus x 2 whole square, and where beta x bar lambda x will tend to 0 as lambda tending to 0. So, this is by the definition of twice differentiability of f at x bar. Now, let us try to simplify this expression. Now, since function is still we have not used the convexity property of the function f. So, let us try to use it. So, since f is convex on S, so this implies f of x bar plus lambda x minus f x bar is greater than or equals to lambda x transpose gradient of f x bar. This is by that property which we have discussed in the last lecture, that if function is once differentiable, then this property holds. Then we can say that f of x 1 minus f of x 2 is greater than equals to x 1 minus x 2 whole transpose gradient of f x 2. So, this is by this property if function is convex. So, here x 1 is this, x 2 is this. So, it is x 1 minus x 2 whole transpose gradient of f x 2. Now, if we club this expression with the previous expression with this expression. So, this minus this is greater than equal to 0. Okay. So, this means this expression is greater than equal to 0. So, if you club these two expressions, what we get finally? Now, using the above expression, suppose this expression is 1, this expression is 1, okay. Suppose this the above one, suppose this expression is 1. So, using this expression in 1, we get 1 by 2 lambda x transpose gradient square f x bar lambda x plus beta x bar lambda x norm of lambda x whole square is greater than equal to 0. Now, lambda is a scalar, so can be taken out. So, lambda into lambda square, and lambda can be also taken out from the norm. So, lambda square can go can be removed. So, this implies 1 by 2 x transpose gradient square of f x bar x plus beta x bar lambda x norm of x square is greater than equal to 0. Now, take lambda tends to 0 plus. So, if lambda tends to 0 plus, this will tends to 0 as per definition of twice differentiability of f, and so this will be greater than equal to 0. So, take lambda tending to 0 plus, this implies beta x bar lambda x will tends to 0, and hence x transpose gradient square of f x bar x 1 by 2 will greater than equal to 0, which further implies x transpose gradient square f x bar into x is greater than equal to 0. So, we have shown that for any x belongs to Rn, this expression is greater than equal to 0, that means this matrix is positive semi definite at x bar, and x bar is a variable point that we have already taken as a variable point. You change x bar, so that means it is positive semi definite for every x on S. So, one part of the proof is over, that if f is convex, then Hessian matrix of f is positive semi definite for every x belongs to S. Now, let us try to prove the converse part. Let us take f this is positive semi definite, and we will try to show that f is convex on S. So, let us try to prove the converse part. Now, let gradient square f x is be positive semi definite for all x belongs to S. So, we have to show that f is convex. So, let x 1 comma x 2 belongs to S. Okay. So, by the mean value theorem, what we will be having? F of x 1 minus f of x 2, f of x 1 is equal to f of x 2 plus x 1 minus x 2 whole transpose gradient of f x 2 plus 1 by 2 x 1 minus x 2 whole transpose gradient square of f x cap and x 1 minus x 2, where x cap is some convex linear combination of x 1 and x 2. Okay. Now, since this is positive semi definite and x 1 minus x 2 is any vector in Rn, so this quantity, of course, this x cap belongs to S because S is convex, and x1 x2 is in S. So, x cap is also in S, and this is positive semi definite, and x1 x2 is any vector in Rn. So, this part is greater than or equal to 0. Okay. So, we can say that x1 minus x2 whole transpose gradient square of x cap x1 minus x2 is greater than or equal to 0, since del square f is positive semi definite. So, this implies if we apply this inequality in this expression, finally what we get, f of x1 minus f of x2 is greater than or equal to x1 minus x2 whole transpose gradient of f x2, and which by the property of convex function implies f is convex. So, so we can say that we have proved this theorem, this theorem that f is convex on S if and only if Hessian matrix of f at x is positive semi definite for every x on S. Okay. Now, let us discuss one example based on this. Suppose you are having this example. Suppose f is from R3 to R, and f x y z is given by this. Plus 2 x z. Now, we have to see whether this function is convex or not. How we will see? We will find the Hessian matrix of this f, and using the test, either eigenvalue test or minor test, we will try to see whether the Hessian matrix is positive semi definite or not. If it is positive semi definite, then we can easily say that this function f is convex by the twice differentiability property of f, convex property of f. So, let us find Hessian matrix of f. So, Hessian matrix we already know how to find. It is del square f by del x square, which is 2 x. Okay. It is second derivative. So, first you find f x. What is f x? F x is 2 x plus 4 y plus 2 z. What is f y? F y is 8 y plus 4 x plus 4 z. What is f z? F z is 2 z plus 4 y plus 2 x. Now, we have to find it is f x x, it is 2. Then del square f by del x del y, which is 4, x z is 2. So, it is also 4, it is 2 by the symmetric property, because this is always symmetric. Then it is 8, the second derivative, this is 2, and x z is, and y z is 4. So, it is 4, it is 4. So, this is the Hessian matrix of this f. So, let us compute all the principal minors of this. First of all, minors of order 1 cross 1 again. So, we have already seen minors of order 1 cross 1 are nothing but diagonal elements. So, diagonal elements here are 2, 8 and 2. Okay. Now, minors of order 2 cross 2. So, how to find minor of 2 cross 2? You delete, suppose you are deleting third row and third column. What left with us? 2, 4, 4, 8, the determinant of this. Then suppose you are deleting first row and first column. So, it is 8, 4, 4, 2. Then okay, second row, second column is left here. Second row, second column is nothing but 2, 2, 2, 2. Second row, second column 2, 2, 2, 2. So, what is this determinant? 16 minus 16 is 0. Here 16 minus 16 is 0, and this is also 0. All minors of order 2 cross 2 are 0. So, let us compute minors of order 3 cross 3. Minor, only one minor is there. Minor of order 3 cross 3 is only 1, which is a determinant of this matrix, determinant of Hessian matrix, which is equal to what? So, it is 2 times this row, this 16 minus 16 is 0, it is minus 4, again 16 minus 16 is 0, plus 2, again 16 minus 16 is 0. So, this is also comes out to be 0. So, now here all the principal minors are greater than or equal to 0. See, 1 cross 1, 2, 8, 2, 0, 0, 0, that means all principal minors are greater than or equal to 0. So, what we can say about the Hessian matrix of F? So, this implies Hessian matrix of F is positive semi definite for every x, y, z belongs to R3. And by the by that theorem of convexity, we can say that F is convex function on R3. So, in this way by simply find the Hessian matrix of F and check whether this matrix is positive semi definite or not, we can easily conclude that a given function is convex or not. So, this is a simple exercise that how we can find out how we can see that a given function is convex or not if a function is twice differentiable. So, in this lecture we have seen that if a function is twice differentiable, then simply finding the Hessian matrix of F and checking the positive definiteness of that Hessian matrix, we can simply conclude that a given function is convex. Simply similarly, if you want to conclude a given function is concave, then on the same lines we can say that a function is concave on S if and only if the Hessian matrix of F is negative semi definite for every x in S. Okay. So, we will see some more properties of optimization, constraint on unconstrained optimization on the next forthcoming lectures. So, thank you.